Sebastian Schrittwieser.
Okay.
He's a senior researcher and lecturer at the University of Vienna for a lot of different studies all around information security and informatics. And he has quite a large research group, if I'm correct. You have around 10 researchers in your group, something
10.
around that.
Around 10, yeah.
And he does also new research topics all about automotive security and how to secure all the different software parts in cars and also production systems. So if you want also to talk with Sebastian about that matter, find him in the break or engage him also via mail. You will find him on Twitter as well as over our website, as far as I know. So, welcome, Sebastian. Thank you for taking your time for us and for the talk, Attacking Mobile Apps Through Network Analysis.
Okay, thank you.
Thanks.
Thank you. Yeah, it's great to be back at a real conference with real people. And I once submitted this a topic as related to this as a paper to a conference, and one of the reviewers wrote, well, that's a fun little paper, and I don't know if this is good or not, if this is a compliment, a fun little paper. It got accepted anyway, so at least it was good enough for them. But that should be also the motto for this talk. So a fun little talk about what happened in the past years in mobile app security and what we saw, what could go wrong if you don't think about security in mobile app development. Okay, and before we start with mobile apps, I would like to show you a website you might know, at least you had to register for the conference at some point. And if you look at web security compared to security in mobile apps, everything is transparent. So you can open a web page in the browser, you see a URL bar, so you see where the requests go to. You have link targets with mouse over, and you even have this huge web inspector where you can see everything what's going on in this communication between the web browser and the web server. And that's something which gives you a lot of transparency. So the communication between the client, the web browser, and the server, the web server, is very transparent to the end user, and you can look at everything. And hiding something inside the protocol is not really feasible, because someone will find out by just looking at things you see in the web browser anyway. So you don't need additional tools and nothing. So something like insecure direct object references that we have in the OWASP top 10. This is something that you might notice quite early. That's something like invoices that just count up. That this is not a good idea because you could guess these IDs. Of course, it still happened, even to some bigger companies that sell phones and computers like this one that had exactly this problem a few years ago. But anyway, so you see it's transparent, and you might notice problems before it gets a bigger problem. So when we now look at this communication between the web server and the clients, the web browser, I always define it as very little program logic that happens on the client, on the web browser. It got more over time with heavy use of client-side scripting, JavaScript, but still data is most often delivered as, I call it, instant meal, and the browser is just a presentation layer that then shows all the data. Compared to apps, it's now that the phone is more complex, and more complex operations on data can be done on the phone. And often just raw data is sent to the phone, and then the program logic is mixed up with the presentation layer, and calculations are done on this raw data and then presented. And sometimes, because you can't really look inside, developers of mobile apps design their communications protocols in a way that it's insecure if you know how this communication actually works. And you might find data that is transferred over the network, hidden from the normal user, that shouldn't be there, actually. And I would like to go with you through some of well-known and not so well-known apps, and would like to show you what happened in the past years and what we saw in our research. At the end, we'll also look at what could have been done better. For some of them, it's quite obvious that this is not a good idea how to solve this. For others, it's not. So let's start with the first app, Tinder. You might know. What happened there a few years ago, so the Tinder app shows you the distance to the owner of a profile you're looking at. And in an earlier version of Tinder, it looked like this, that the data came to the client in nice JSON. You had things like the birth date of the owner, the gender, the name, and everything. And you also had the position of the owner of the profile. And it was quite accurate and a little bit creepy, because the app, of course, didn't show you the exact location of the owner, but just something like 3.5 kilometers or so that you can't really know where exactly the other person is. With this information that is also transferred over the network, you knew exactly where a person was, down to one apartment maybe. And that's a little bit creepy. And the problem was that the raw data was delivered to the client, and afterwards, on the client, the program logic then calculated the distance by just getting the own location via GPS, and then just calculating the distance and presenting it on the profile page. This vulnerability was then reported to Tinder, and it got fixed in a way that just the distance in miles was then sent to the client, and this was then presented. Of course, it was not presented in this accuracy with 15 digits, but just something like rounded to 5.9 miles. Why 15 decimal numbers? It's also raw data we don't really need. Well, for everything there's an XKCD, and we can look up what 15 additional numbers exactly mean. So we don't need to track them down to atoms. So maybe this was also some kind of mistake. It's quite funny that this happened, but what could possibly go wrong if you present a distance in this accuracy? You can triangulate someone. So what was done then, people did a few measurements. So you can also, of course, fake your location, so that's fast and you don't even have to go outside. And it was possible to pinpoint profiles down to, I think it was then 10 meters or so. Again, not that good. In the end, they fixed it again and then rounded it to the exact same accuracy that was then used in the app to actually show in the profile. Okay, let's look at another type of apps. This is a really strange type of apps, actually. So one of them is SuperSwap, but there are several others. And the basic idea of this really strange apps is you take a picture, and someone in the world with exactly the same app also takes a picture at the exact same moment, at least that's what they state, and you swap these pictures. But without knowing who the other is. So you can't send text messages, you can't store this contact, you can just reply to someone else. You can imagine for what kind of pictures this is used, but anyway, we were interested in if it's really a picture that was taken at the exact same moment, or if they just show you some old pictures of someone and they hope that this other person then interacts with you and sends you a picture back and so on. So we looked again at the communication between the server and the client. For one of them, the URL structure looked like this. Actually, it looked not like this. There's an S after HTTP. It was without. But anyway, let's say it's like this. It doesn't get better with encryption. So what you can see is it was stored on some server and on directory images. And yeah, the one picture we got was something like a number. And then we took another picture, and there was again a number that was a little bit higher, and we thought, well, there is something fishy going on, and yeah, we tried to build a complex program that downloads all the pictures. It looked then like this, and it took us maybe an hour or so to get all of them. As I said before, interesting pictures, but what was really interesting, we looked at the first 200 pictures, and we saw a pattern. So we looked at them, a computer, a room we saw quite often, keyboard. And we had an idea of who this person could be that created the first 200 pictures in this application. That, by the way, was Xcode, so development. So yeah, let me introduce you the developer of this app. Created or tested the app with the first 200 pictures. After that, some other people started using the app for other things, but before that, the developer, yeah, took pictures of the entire flat and around and everything. Yeah, then another type of another app of this type had this kind of file names of the pictures that were sent, and it was also interesting. At first, it looked more random, but then we found out IP, WP, and nothing. It was the phone type, so iPhone. They had even a Windows Phone app, and nothing was Android, because this was the first app that was developed, and afterwards they decided, we have to add the phone type as well and edit them. Then we had the hardware ID, and at the end we had a timestamp, so we knew exactly when the pictures were taken. Of course, they were not taken at the exact same moment. We just got any random picture out of this huge pool. What was also interesting is that for this there were two requests, basically. One was, I send you a picture, and the other one was, please give me a picture from the network. And the great thing was, you don't have to send actually pictures, so just doing the request, please give me a picture, 1 million times got us all the pictures that were randomly then delivered to us. No, absolutely not. We just got some pictures more than once because it was random, and in the end not that big. There were around 700,000 pictures or so inside there. Another example with a similar problem with independent requests for things that should be atomic from a security perspective. That's Snapchat, you know, this nice app where you can send pictures to someone and they get destroyed after some time, let's say 10 seconds. And if you look at what actually is done on the network when you send a picture, or when you download a picture, basically, is at first there's this updates request, so the app asks the server, hey, is there a new picture for me? If yes, then it gets downloaded, that's the blob. It's encrypted, the key is stored somewhere in the app. It takes you around 30 seconds to extract it, but that's again another thing. And then you can look at the pictures, or the picture, and after 10 seconds, the phone initiates these update snaps, which basically just says, please delete this picture on the server. If it's deleted, we don't know. At least it's not possible to download it again. But what you can do is, you can just don't do this last update snaps. Then it doesn't get deleted, and you can download it again, because it's a separate request, and you don't have to do them both. So what happened then, of course, there was something like this, Snap Save, a web page that you trust to give the credentials of Snapchat to it. It downloads all the pictures for you, but doesn't do this update snaps. So you can use the Snapchat app independently from this. You just store the pictures. And if you allow something like this, then of course something like this happens. So thousands of these photos and videos were released on the internet. Of course, it was not the Snapchat server that had vulnerability. It was one of these SnapSave and other services that stored hundreds of thousands of pictures without protecting them properly. And yeah, first people thought, well, it's a problem of Snapchat, but no, it wasn't. It was actually one of these services that had the problem. And then with WhatsApp, WhatsApp was really interesting in the first years when they had already hundreds of thousands of users in Austria and millions around the world. It was a really simple system, at least server side. And as you can see, just a few PHP scripts server side that did the authentication inside for WhatsApp. And the funny thing is, if you first launch WhatsApp, you have to type in your phone number, and then they send you an SMS. And in the SMS, you have a PIN code that you have to type into WhatsApp so that your phone number gets verified. If you type in the phone number of someone else, of course, this SMS does not get delivered to you. You don't have the PIN. You can't hijack the account of someone else. That's good. What happens, or what happened, if you typed in your phone number in WhatsApp and then said, press the button, give me the PIN code, it sent a request to the server with your phone number, so the two. Again, the phone number in and the country code also twice, but anyway, a hardware ID, of course, that WhatsApp can track the devices, I don't know. And there was an auth PIN. It was 3 digits. Nowadays, I think it's 6 digits, so WhatsApp found out that 3 digits is not quite enough for this security code. But this was actually the code that they then sent you via SMS back to the phone. So what did they do? They created the code on the phone. It was sent to the server created an SMS, sent it back to you, and the phone verified itself if it's the correct PIN. With this knowledge, of course, it's easy to hijack accounts within seconds. Another interesting problem they had the status messages. So before this WhatsApp status we have now, the one, the clone from Instagram. There were text status messages. I think it's still possible to do them somewhere in the settings. And this was the request for modifying your status message. So you have to provide them with your phone number and with your new status, but nothing else. So the request was actually exactly this. And another research group also found out that this is not that good. that there is no kind of authentication, and you could change the status message of anyone. You just have to know the phone number. And they told this WhatsApp. WhatsApp ignored it. Same with us. So I once got a message from them, but too late. And what this other research group then said, okay, well, let's increase the pressure. They created a website. It was called whatsappstatus.net or so, and you were able to change the WhatsApp status of anyone. So it had just two form fields. One was the phone number, and the other one the new status, and yeah, update it. And of course, this caused a lot of media attention. And after 1 or 2 days, it didn't work anymore. And everyone said, oh, well, they fixed it somehow without an update of the app. Interesting. Let's look inside. The protocol was still exactly the same. And then they found out they just blocked the IP address of this service. After that, this research group said, okay, here, that's a Windows app. You can do it from your own computer with your own IP address. Have fun. And after that, they fixed it by checking more or less the IP address from where this request comes from. And if someone is logged into WhatsApp, so that was in the background an XPMP account, if this was the same IP address, then it was okay to do this modification of the status message. So still not nice, but better than nothing. Nowadays they actually changed it. And another interesting thing that still kind of works is how all these messengers actually work and how they find out to whom you can send messages to. So what they do is, at launch of the app, and every time you reload the contact list, they send all the phone numbers of your phone books to the server. The server has a huge list of all registered phone numbers that have WhatsApp registered, installed, and they send you back a subset of all the accounts to whom you can communicate via WhatsApp. So in this case, they send you the phone number, then some kind of T, this was a timestamp when you were last online, and a string, that's the status message, and then some ID, that's again the phone number. And with this knowledge, of course, you could send WhatsApp large phone books, like all the numbers of an entire country. So for Austria, that's around 40 million phone numbers, a little bit more for all the smaller virtual carriers, but for the bigger ones, let's say 30 or 40 million. And we did exactly this, so we sent them, all of them. At first, my naive approach was I put all these phone numbers into my my address book on the computer, then I sync it to the phone, launch WhatsApp, and it will upload 10 million phone numbers or so, and everything will work. Of course, it didn't. It crashed my phone because 10 million phone numbers is not okay for a phone. What we then did is we implemented basically the client and sent 5,000 phone numbers in each request. After a few seconds, we got the subsets back, and we did this for several hours to get all the phone numbers. And it was interesting to have all status messages of everyone in Austria, or in this case, in the United States. You find really interesting and funny things. What people write if you have hundreds of thousands of these status messages. Yeah, and you might now say, well, yeah, four examples of apps where things went wrong. The thing is, there are endless examples of these kind of problems. So we had an audio streaming app that offered offline listening, and I was interested, how do they store or download these files? Actually, it was a publicly accessible URL with the unencrypted audio file that you could just download, and yeah, you were able to download the entire streaming service with this knowledge. So absolutely no protection. There are small games inside an app of a well-known fast food brand, at least in Austria. They give you these games, and then you can win French fries and burgers and stuff like that. And it was just JavaScript written games that were transferred to the client. It was obfuscated, but all this online deobfuscator just deobfuscated it within seconds, and it was quite easy to modify this and eat more burgers than it would actually be good for you and your health. There's a ticket app for public transport in a European capital, and they showed you the ticket on the phone with some security features like distorted text in the background and some clock that is animated and stuff like that. So they tried to implement the same security features you have on a physical ticket to make it harder to forge. But the problem was that all the ticket data, like customer and the date, the type of the ticket and so, this was sent separately over the network to the client, and then the client afterwards created this ticket with this stored text in the background and everything. So on the network, it was quite easy to just create a ticket for the next day without paying, and it looked like a valid ticket then. And there was a multiplayer online game where a variable for calculating bonus points was sent to the client from the server when it was launched. And there was this bonus multiplier. This was 10. Changed it to something a little bit higher. And it was quite easy to win the game afterwards. So in almost any app you look, you find something that is hidden inside these protocols that you can't really see. But if you make them visible, you can have a lot of fun, and it's interesting what happens. So what are the countermeasures? I just told you what went wrong in the past. So I often hear something like, my traffic of my web application is encrypted anyway, so nobody can look inside. The problem is this is transport layer encryption. So it's encrypted between your server and the phone, but you can break it up. You can do a man in the middle. If you are the owner of the phone, which means that it's not that hidden as you might think, or might developers think. You now argue, what about certificates? They should prevent exactly this kind of man-in-the-middle attacks. Well, yes, they should work like this. So you have the encrypted connection, you have some trusted third party, and the trusted third party issues a certificate for your web application. It's sent to the client, and then there's a trust relationship, and if it's a trusted certificate now, then it's not possible to just forge this online service in the background, because the certificate wouldn't match. So the goal is here to ensure that the client communicates with the right server. The problem with these analysis we just saw in this talk is that you have another type of attacker. So the attacker is not on the internet. The attacker, that's you, or that's someone who wants to analyze the app. And this attacker sits on the phone or on the local network, but has access to the phone. So now a root certificate is issued to the client. In a normal use case where I want to protect communication on the internet, of course, you can't install this root certificate on the client. If you want to do such an analysis and want to reveal how these protocols work, then you can do, because that's your own phone. So you install it, it says, that's trusted, and with this, you can communicate with the man in the middle. So the second goal here should be to ensure that the client does not connect with the wrong server on purpose. And that's not that easy. There's something, certificate pinning. So my app checks a particular certificate, and if this particular certificate is used, that's good. So this increases definitely the security. It reduces the costs. I might argue, let's encrypt is free, but still it's not valid for that long. You have to change the certificates on the client or the checks, so less flexibility. But some aspects will prevent these types of attacks. But if the attacker, the analyst, has access to the phone can be modified in any way. And for example, there are this SSL kill switch for iOS, and there's this Just Trust Me extension for Android phones that allow you to just remove these checks system-wide. So you would have to do the checks directly in your app with your own code without relying on system functionality to actually prevent this or make it more reliable for certificate pinning. So certificate pinning basically relies on a trusted client, which we now know does not exist. So what could you do? The only advice I can give, never ever trust the client. And in this case, even if it's your own client, you might say, well, it's my client. I know what I'm doing. Yeah, but it could be modified, and then you don't know. I know this advice is old. We hear this every time we talk about server-client communication, but it's still a problem. And every time we have some new systems, in this case, mobile apps, all the same mistakes done over and over again. And it took more than a decade to have more and more secure apps we see nowadays. So what could have been done in the 4 apps I introduced today? So for Tinder, it's obvious, don't send data that you don't show anyway. So if you don't show the coordinates, and you don't have to show the coordinates, then don't send them. And if you send data, don't send them that precise or not more precise than they should be. For these photo swapping apps, don't make URLs guessable. I think that's obvious. And don't reveal more information through the URL, like the phone type, the email, and stuff like that, if you don't need to. For Snapchat, secure the protocol against control flow logic attacks. So in this case, it was possible to just do the one request and ignore the other. This shouldn't be possible. And for WhatsApp, don't perform security critical operations on the client. So don't create this PIN code on the client. And of course, don't check it on the client. So the client verifies itself. That's absurd and doesn't make any sense. Perform user authentication before executing an operation. So perform user authentication before you actually change the status message of someone. And of course, rate limit your APIs. It shouldn't be possible that I upload a phone book of 30 million entries within 3 hours and nothing happens, although they detected this problem. So they had a Twitter account during that time and said, yeah, we have problems with our servers and we're rebooting them. And so this was maybe our scanning, but they didn't block us. Yeah, I think we are at the end of time. So thank you for your attention, and there are questions, just ask.
Thank you, Sebastian, for this awesome talk. We have a few questions here. So the first one would be, it looks like mobile apps are like the Wild West in the security context. Why can't such apps be even in the App Store, like Apple's App Store or Google Play Store?
Yeah, so this is not something that is actually tested when these gatekeepers of Apple and Google check the apps. So what they don't want in their apps is they ban content they don't want to see, and they look if private APIs are used, basically. But they don't really do security checks of the apps. They don't check how these protocols work. They just ignore this fact.
Couldn't there be any kind of responsibility like pushed over to Play Store or App Store from Apple? Then that matter actually because they're providing the app or giving access at least to the app?
I don't know how this is from a legal perspective, but yeah.
Right.
Maybe not.
Do you have any experience with the private contact discovery in Signal? Is it any better?
Yeah, so private contact discovery works in, so at first they just upload hash values of the phone numbers. This is good, but not enough, because the number space of possible hash values and phone numbers is too small. So you can create rainbow tables and then reverse them. What Signal actually does is they have code running on their servers that you can remote attestate. So you see the code in their repository, and if you think this is something that is secure, then you can verify that exactly this code runs on their machines. And if you assume that this hardware protection, it's Intel SGX, is secure, then you know that exactly this code is running. The problem is SGX is not really secure, so there are many attacks on this, and you still have to trust Signal that they don't use one of these vulnerabilities to hiddenly modify the code and don't delete phone numbers after lookup. But yeah. It's tricky. So there's no real secure protocol for this phone number matching without giving trust to the operator or trusting some type of hardware system.
It's almost the trust in third-party system. Right?
Yeah.
So last question. How useful are in-app protection solutions for obfuscating, securing a mobile app?
So Android apps, for example, are basically obfuscated in the toolchain itself. Most things that are done is like identifier renaming and stuff like that, so that class names are not visible anymore. And this makes it more difficult to analyze it on a binary or bytecode level for Android and iOS. But the analysis I showed you today is just on the network. So no matter how obfuscated and protected these apps are, we don't have to look inside them. We just look at the communication between the client and the server. You can have an unmodified phone with an unmodified app. Without looking at the app, just at the code, you can do all these kind of attacks.
Perfect.
So you don't really care how protected they are.
No, thank you very much, Sebastian, again, for answering the question and for the talk. If you have further questions concerning maybe the research related to Sebastian, what he's doing right now, or also other aspects, please always engage him in the break.